of what I will talk about today is actually inspired by Dr. Adam Walker, who has this YouTube channel on close reading of poetry. And I didn't know what close reading is. I learned it from him. And one important thing is context. That is what I will focus on today. And in fact, if you were hoping that there will be a whole lot of poetry in this, I might have to disappoint you. This will be more about the history of science and what caused these poems to come into being. So it's more about precedents, really, what I want to talk about today. But what I found on his channel was this quote: "A scientist not only beholds intensely the present as it is and discovers those laws according to which present things ought to be ordered, but she beholds the future in the present. Science awakens and enlarges the mind itself by rendering it the receptacle of 1,000 unapprehended combinations of thought. Science lifts the veil from the world and makes familiar objects be as if they were not familiar." There's a lot that resonated with me, having spent 2 decades or so in science, except this is not about science. The original quote is about poets, and it was written by Percy Shelley, one of the greatest poets of the English language. And that got me to think, why is there so much similarity in what Shelley thought poetry is about and what I thought science is about? So I came up with my own list, and I don't want to dwell on it for too long, but this is a list, as I said, of things that I came up with, why there might be overlap between what motivates people to write poetry and what might motivate us to do science. And I will come back to that at the end. Now, there will be 5 poems that I will focus on, and each of them will be roughly centered on an event or a scientist. So the first one that I want to talk about is Pierre de Fermat. He is famous, or got famous, a couple of years ago because he wrote a theorem in one of his books that finally got proven. A theorem in mathematics is a statement that you know how to prove. So he wrote a statement in one of his books, and then in the margins of the books he wrote, "I don't quite have the space in this book to write down the whole proof." And that must have been an understatement, because the proof happened a couple of years ago, and it's several pages long. So it seems funny that Fermat seems to have thought that he had the proof and he couldn't quite write it down in the margins. It also involves so much modern mathematics that we've discovered since he died that it seems likely that he never was able to prove it in the first place. Whether he thought he had a proof or whether he was aware that he didn't have a proof, we don't know. But this event in mathematics that we finally came to prove this was a big event. And it also triggered this. So this is a special issue of one of the mathematics journals where they inspire people to write poems about it. And in this poem, I would say there's a lament. Fermat's theorem has been solved. What will now make math evolve? There are many problems still, none of which can cause that thrill. So you can almost feel that there seems to be a sense of loss here among mathematicians in terms of now they lost the chance to solve it, or maybe to get $1 million. And I don't actually want to talk about Fermat's last theorem, but about his principle that is more important in physics. And so I'm going to express it here glibly, which is that light travels along the path that takes the least time. This is not quite technically accurate, but this is how usually we teach this to undergraduate students. And it is what can be mathematically formalized as Snell's law or refraction. It is, of course, for me as a vision scientist, how vision begins with the lens. Light gets refracted, it gets bent. And you can see this right here with a piece of glass where the light enters, in this case, a laser beam, and it gets bent. And so what Fermat found out, without having the precision and the help of ChatGPT that I had, that the speed of light inside glass is slower than the speed of light outside in the air. So while the speed of light is constant, that's true for the vacuum. So in other materials, obviously, it can slow down. And that is the case for glass. Now, one way to think about this is that this seems peculiar at first, why the light just doesn't go straight. Why does the light take an angle like that? And so what Fermat is explaining is that since the light is going slower, it will try to get through the glass as quick as possible. And I'm, of course, anthropomorphizing here, but it's taking the shortest distance through the glass to make sure that it doesn't spend too much time in it since it is so slow. And the goal is to go as fast as possible. And so that would not be the case if it goes straight, because of triangle inequality. Of course, this distance is longer than this distance. So it takes a shorter distance. It could be even shorter, So why doesn't it take this distance? And so the answer lies in then in this case, it would have to travel even a longer distance here. So you would have to take the totality of the distance. And if you do the math, it comes out that it's still then slower than the actual path that it takes. So this is it's a big principle in physics. It has been widened to the principle of least action. Some people say that's the only law of physics that we know that seems to really explain everything and hold to everything. It gets even more bizarre when you learn about quantum physics and you learn that what light really seems to do is take all possible paths. So some people have said that's the only general theory of physics that we have. But my point here is something else. My point is that this, to me, is not intuitive. It doesn't seem intuitive to me that light seemingly knows what its speed is in different mediums, that it seemingly knows before it takes the path, which path to take. And so what I conclude from all of this is that intuition is a poor guide when it comes to science. So when it comes to discovering how the world works, one of the lessons that I want to talk about today is that maybe we shouldn't trust our intuition. And I think that goes further. That goes into neighboring disciplines where we think about what could be. So a famous argument that pertains to my research is, what if we know everything about the brain, we still wouldn't understand consciousness? Well, that relies on conceivability. That relies on you conjuring up a future that we don't know what it will be like. It relies on your intuition. And I think intuition is a poor guide. Moving on to the next poem. This is about Isaac Newton, who, of course, might be one of the most instrumental physicists, first physicists. And so he's often shown in this way as the geometer. And actually, the poem I'm going to talk about next is one of my absolute favorite poems. And I'm not going to give you the whole poem, but it's worth checking it out, including different translations. It was written by Edmund Halley, so that's the Edmund Halley, who the comet is named after. It's written in Latin, of course, which was usual at the time. And this is a beautiful translation. Then ye who know on heavenly nectar fair, come celebrate with me in song the name of Newton to the muses dear, for he unlocked the hidden treasuries of truth. So richly through his mind had Phoebus cast the radiance of his own divinity. And here's the sentence that almost give me the chills. Nearer to the gods, no mortal may approach. So this was actually published as the foreword of the Principia, which was Newton's most famous work and most impactful work. There's an interesting story there as well, that back then there were issues with, believe it or not, universities. And the solution of the academics back then was to found a second space where the corruption and a lot of the issues that universities had wouldn't take hold. And they ran out of money to print Newton's book. But eventually it got published with this beautiful Ode to Newton by Edmund Halley in front. And what I want to point out here is when he means nearer to the gods, no mortal may approach, what he's really is saying is that we're getting so much insight here into how the universe works that it seems that there may be more, but that is closed up to us. And so why did they think that? Why did they have such a strong feeling of accomplishment back then that they would write poems, and not even write a poem, but write this about a living person? Now, what Newton said, and I think what allowed him to have this breakthrough, is that he said in philosophical disquisitions, and we should know that back then science was philosophy. So in philosophical disquisitions, we ought to abstract from our senses and consider things themselves. So what he meant by that is a Platonic notion of that you should not take the Aristotelian look at what's right in front of you, but think more about numbers, laws, functions, the things that seem to have no physical existence in the universe. And as we all know, that is what he did. He came up in particular with three equations that are still known as Newton's law. F equals ma, the one that is the most famous and most of us know. But what became clear then, and then even more in the years to come, is that these three equations, they explain almost everything that we can observe in the living world. It took a very, very long time until we found exceptions. And it's, of course, the very, very small, I'm talking about quantum physics, and the very, very large, I'm talking about relativity and cosmology. But everything that happens in this room scale, in the scale of our cities, of our world, can be boiled down, reduced to these three Newtonian laws. We have not found an exception yet. If you can find an exception, you will get the Nobel Prize within months. That is an astounding accomplishment. Why three equations are possible to explain so much about nature and the world around us. And so I will go back to another poetic statement. by Galileo Galilei, who famously wrote, roughly speaking, that the book of science is written in the language of mathematics. A fellow Tennessean living in Oak Ridge, Eugene Wigner, he wrote a very famous paper that is called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. How is it possible that these man-made ideas all of a sudden explain things that we observe in the world? How can it be that if we come up with a crazy idea such that we can take the square root of -1, even though every negative number, if you take the square of it, gives you a positive number? But we came up with this concept that I is the square root of -1 hundreds of years before we found that without it, quantum physics does not work. How is this man-made? What are we really discovering here? And so yesterday I actually watched another video on YouTube where somebody made this very astute observation that when it comes to the way that we teach the Western history, we obviously have Plato pointing up to Platonic ideas and Aristotle pointing down to the real world. It's the old clash in philosophy between the rationalists and the empiricists. And while they argue on seemingly, obviously, beautiful painting that is hundreds of years old, never coming to a conclusion, it's worth looking right here, where the mathematicians are using a compass to answer ideas about the real world by mathematical proof. They come to a conclusion. Third poem I would like to talk about is actually not somebody else writing the poem, but the scientist himself, James Clerk Maxwell. And so Maxwell, of course, you might have learned, used Newton's physics, his 3 laws, and he expanded them into Maxwellian equations. So those are the equations that we use for electricity. James Clerk Maxwell, from all the scientists whose biographies I've read, is probably my favorite scientist. And so I wasn't surprised that he actually wrote poems. And he started writing poems in his early teens. So here's one of his poems. When earth and sun are frozen clods, when all its energy degraded, matter in ether shall have faded. We, that is, all the work we've done, as waves in ether, shall forever run in swift expanding spheres through heavens beyond the sun. This is one of his last poems. And the reason that I want to point it out is that he uses this term ether a lot. And this is actually very key. Most of us don't believe in ether. We've learned that the ether has been disproven. But why was he such a strong believer in the ether? Well, what Maxwell did, actually, is that he focused on earlier findings by Faraday. And so this is probably how most of us have learned this in high school. This is a magnet, and then we take iron particles, and if we shake this whole system, you will find that the iron particles, they will orient themselves around the magnet in these wavy lines. This is how we usually teach the magnetic field. And Maxwell formalized the mathematics behind how this works and how electricity relates to that and also can create these fields. In fact, that was Maxwell's actual contribution. Faraday had almost no schooling, and he knew very little about mathematics. The reason that Faraday was so successful, he's a lab rat. He was experimenting. And it was a time in Victorian England where electricity came along, and he could have these shows, almost like magic shows, where he would have these arcs and, yes, Faraday cages, and he would travel around the country. He was also very handsome, it didn't hurt, and had these shows where people paid a lot of money, and he would have these public lectures about physics. And indeed, the Royal Society built an auditorium that stands today still, and has still these public lectures that you can find online in this tradition. But he couldn't describe this mathematically. He showed something really astounding here, because if you really think about what's happening here, let's go to Plato and Aristotle again, that what we really only observe is iron particles. Now, what we use to explain why the iron particles are ordered in the way that we observe them is that we now use this notion of a field, which goes back to Faraday, because he had no other language to get at that. But we cannot really see the field, can we? We really just see the iron particles. The field is something in our mind, something Platonic, that we use to explain why the iron particles orient themselves the way that they do. And that caused a lot of tension, because it seems that now we have physics without particles. There's something else. And for Maxwell, that must have been the ether. So indeed, in his theories, he came up with this idea that there are still tiny little ping pong balls that are causing all of this. And those are the ether. So he had this idea of a mechanistic ether, where if you see things interacting at a distance, where I can't explain how one particle bumps into another as in Newtonian physics, it must be that in between are tiny invisible particles. And there's a chain reaction, domino stones falling of this bumping going on. And Maxwell's real contribution here was that he was an excellent mathematician. In fact, when he went to Oxford University at the time, the exit exams were so difficult in mathematics that when somebody solved the exit exam after going to college, they had from the newspapers in England, cartoonists come and draw a sketch of the face, that was before photography, of the student who managed to do it, and it got published in the entire British world. And so I've heard from colleagues that if you take these questions that they used in these exams and give it modern mathematics professors, they struggle. That's how good he was in mathematics, and it took ingenuity to explain what Faraday showed us by showing it, by demonstrating it, and to formalize it and explain it mathematically. But what he didn't realize is you do not need any ether for that. And we now know that, of course. And that is a profound change in how we do things, or think about things in science. Because up until this point, the leading theory was John Dalton's. And it's a theory that I actually believed until a couple of years ago. So what is it? It's the mechanical model that John Dalton proposed, who started with the atomic model. And it can be summarized as that the properties of matter can be explained in terms of the sizes, masses, and motions of indivisible particles or atoms. In other words, the universe consists of time and space, and in there you have particles. And what you observe are their motions and interactions. And as I'm talking to you, of course, you do not see how the sound reaches your ear, but you're assuming that there's tiny little particles in the air, they bump into each other, and that bumps eventually a tympanic membrane, and that causes the vibration that gets translated in neural activity, so you hear. But if there's no ether, then how do we explain these fields? How do we explain those seemingly without particles existing physical effects? And so that has caused a change in the philosophy of science. And so a scathing critique of that I read a couple of years ago that I like is by James Ladyman, who makes fun of this idea and calls it microbangings. The idea is that the whole universe comes about by microbangings, these microbangings between these tiny particles. And Maxwell's mathematics leads us away from that. It explains fields and how they come about without particles. You do not need the ether. So in this biography that I read, there's this beautiful sentence that says, all we know about the foundations of physics, possibly all we can ever know, there's this no closer to the gods no mortal may approach, are their mathematical relationships. And here it is. Maxwell had dispensed with the need of a mechanical model. So this was actually a huge point in physics where physicists had to become content with the fact that the math explains something and you cannot imagine it anymore. And let me bring that home. Let me make this really strong. So when it comes to radioactivity, which is of course something that we discovered much, much later, if we take, let's say, a piece of uranium and we put it in a cloud chamber. A cloud chamber is basically just a chamber. And then what we do is we put dry ice or something very cold at the bottom, and we put ethanol at the top. So it builds a temperature gradient. And then you put a little bit of water vapor in that. And what that causes is that water has this weird property that if you cool it down below 0 degrees Celsius, where it should freeze, but you do it very carefully so, it becomes a liquid. It stays a liquid, but at any point, if it gets rattled or shaken or vibrates, it turns into ice. So you get this mist in there, this water vapor, this mist, and that allows these particles that we cannot see because they're so small, in this case, mostly alpha radiation, it caused them to become visible because the water basically becomes to ice, right, where the particle goes out. And what I want to point out is this looks like particular trajectories, no pun intended. It looks like particles that are expanded. And that seems to go with the mechanistic model. That goes with this idea that, yes, there are microbangings. I can see them right here. But we all know, of course, that this later got severely challenged with the double slit experiment that most of us learned, which is where you can take individual particles, photons, electrons, and you can take one at a time and shoot them at a double slit where it could go either left or right, and then you see what happens at a screen at the back. This is very similar to the actual data if you use electrons. Photons are too small that you can capture individual ones. But it works with electrons. And so if you look at this, is that you find what we now know as interference pattern. And indeed, if you look very carefully, what you find is that happens for single electrons. So this is where it gets mind-boggling. So what you find is that if a single electron goes to either or the left or the right slit, what you actually find, it goes through both. And the reason that that's the case is because we find these wavy lines behind it. We do not find a dot, we find wavy lines. I want to introduce you to an experiment by Anton Zeilinger. So he's a physicist living in Vienna, got the Nobel Prize in 2022, and not even for what I will show you next. This is just one of the other things he did. So his idea was the following. He came up with these chemically constructed molecules. It's a C60 molecule. We call it a fullerene after Buckminster Fuller, who was the architect who came up with these very similar kind of constructions. It's called C60 because it has 60 carbon atoms, and it roughly looks like a soccer ball. And because there's a lot of nanocarbon technology going on, you can construct these in the lab. Now, what Anton Zeilinger and his team were interested in is, if I shoot this at a double slit, can I shoot one through and it interferes with itself? Now, of course, that makes no sense. If you think of it exactly as I'm showing it right here, it's a soccer ball. It should not go through two slits at the same time. I can't go through two slits at the same time. Here's the data. It interferes. So this is wrong. Or at least we have to rethink. Molecules this size also interfere with itself. Now, if you learn about quantum physics, that's not surprising, because this is not what quantum physics tells you. Quantum physics tells you that everything is a wave. The Schrödinger equation is a wave equation. And of course, it works for these large molecules as well. In fact, we struggle to understand where this may be end, because clearly we can't go to the double slit. This was a very key experiment. So I want to rephrase a sentence that a lot of people have heard by Theodor Dobzhansky. Nothing makes sense in biology except in the light of evolution, and make it a little bit broader. I think that nothing makes sense in science except in the light of mathematics. And what it really means is, so I've got to go here to this famous painting, the Flammarion engraving. We don't know who came up with that. It's, if we really are rigorous, if we really think hard, if we are really skeptical and only let the data speak for itself, if we're empiricists, it seems what we really find behind it all is structure, pattern, mathematics. And it's not just me who had this thought. This is from a particle physicist who took a very similar view that once you learn into, and don't worry, I'm not going to talk about quantum chromodynamics or quantum field theory, but once you get to that level, there are no more particles. Now, second to last poem, how do we get there? So I have to go all the way back to what a lot of people see as the starting point of modern science. And it often gets dated back to Galileo and his fight with the Holy Inquisition. So you see this famous painting right here. The story is that Galileo got access to one of the first telescopes, and he saw that there are moons around Jupiter. Now that was a problem if you think that everything in the solar system rotates around the Earth. And he could tell that those are moons because they're bright. You can see them actually with a pretty cheap Amazon telescope. They're nice to look at. But you can see that every night they move, and they clearly rotate around Jupiter. Now the poem I want to talk about, this is really peculiar, because this is the story we usually learn. That Galileo used a telescope, he saw the moons of Jupiter, and he thought, this is so compelling, let me put it in the middle of St. Marco Square in Venice, and anybody can look. Just look, you see the moons of Jupiter. And the story goes, we do not know if that's really true, that the bishop said, I'm not going to look. They refused to look. That's the story. What actually happened? So here is again another Latin ode. And so one of the English translations is, exterior radiance does not always mean interior brilliance. Consider the dark blemishes on the sun. Who would have believed it, revealed by your craft, Galileo? So he did not only find the moons of Jupiter, he also found sunspots. And so this inspired this poem. And there's an interesting story to this poem. This poem was written by Cardinal at the time, Maffeo Barberini, who then becomes Pope Urban VIII. That's the Pope that Galileo clashed with. So what happened here? So Pope Urban clearly likes Galileo. He clearly likes Galileo's science. He wrote a poem for that when he was young. And then this happens that gets Galileo into trouble. So let me tell you before we get to that, what happened. Pope Urban gets under pressure, and they say what Galileo is saying, and it's what you all learned, that no, not the Earth is at the center, the sun is at the center. The real debate was not about that, by the way. The real debate is whether the Earth moves. Comes to the same conclusion. Galileo said the Earth moves. He was wrong, by the way. He thought that the tides are evidence of that. He probably already knew better. So Galileo gets invited by this guy who wrote a poem about him. And Pope Urban at the time says, why don't you write another book? And in this book, you make the point that whether the Earth moves and the sun doesn't, or whether the sun moves, that's just different ways of looking at it. Now, Galileo goes, he writes that in his book, that gets him into trouble, because the character that takes that stance is called Simplicius. That means the simple-minded one. What happens next? Most of us know Pope Urban VIII overseeing the Inquisition. And so this is not the Spanish Inquisition. This is the Inquisition at the time. It's not quite as brutal. But what they do is they take Galileo under house arrest. And so house arrest, again, he had a pretty big estate in the countryside. It's not nice maybe to be far away from the city, but he died there. He couldn't leave. This is a very famous painting that you might have heard about, because in this painting, there's this famous etching in the wall that says, "Eppur si muove." And yet it moves. Because, again, the debate was about the Earth. But when I was in Italy 2 years ago, I was astonished it goes even further. So for some reason, when Galileo died, somebody took his middle finger, put it upright, and orients it in the museum in Italy, maybe pointing towards the Vatican still. So I want to talk about Galileo, but not about this. I will come back to this, what Galileo had there. But before I do that, I want to have an episode about Galileo, why I think that Galileo indeed is very crucial. And there's maybe the biggest lesson today to take away from Galileo. So this is a different episode. Galileo writes a letter in 1604 to Paolo Sarpi, who I had never heard about before. He's another Renaissance man. And they were friends at the time. And so what Galileo writes, they have this debate, as gentlemen do, about this question here. The velocity of a freely falling body, does it get faster and how? And so what Galileo tells his friend is, this is the principle that he says, the velocity of a freely falling body increases in proportion to the distance it has fallen from its starting point. I want you to note this, in proportion to the distance. That was actually not just an intellectual exercise. So at the time, people came up with these constructions to build piers and other things. And what they had to do is they had to ram these wooden poles into the ground. And so for that, they had to find out how heavy and how far and how fast this would move. So it was a practical physics question. And so his proposition was double the height and the final velocity will be double. That comes out of his principle. Actually goes all the way back to the ancient Greeks. It wasn't really his idea. But so he was a scholarly man. That was the meaning at the time. Now, another really interesting person that lived around the time of Galileo, didn't really get along with him, supposedly. My favorite philosopher by far is René Descartes. And so there is this interesting story right here where Isaac Bachman, a friend of, actually a benefactor of René Descartes, he has these discussions with René Descartes. He's saved from the Inquisition. He goes to the Netherlands where the Catholic Church has no reach. And so they have a similar interaction. So they ask the same question. And so he basically asks him, so what do you think, how it falls? Isaac Bachman asked, when can one determine the distance the stone will fall in 1 hour if one knows how far it falls in 2 hours? And so the answer of Descartes is, the solution is that the velocity is proportional to the distance fall. So it's the exact same answer that Descartes is giving. And so again, the reason is this goes back to the schooling. They were even drawing it out with the distance. And the interesting thing is, Beckmann wrote a diary. He goes home and he writes down, I talked to Descartes today, and he wrote the space traversed in 2 hours doubles the proportion of time. So he completely misunderstands, because they said by the distance, not by time. But it turns out he's the only one who got it right. So what is actually happening here? So the original proposition is that the velocity increase is proportional to the distance. And this is a little bit of a subtle difference, of course, that I'm talking about. But if you think about it, it means that the further it falls, the faster it goes. And then the faster it goes, the more distance it covers. And then each step, it means it gets faster and faster and faster, kind of exponentially. So you get this feedback loop of more velocity, even more velocity, yet more velocity. And what comes out of this is this idea that when it comes to acceleration, which is the change of velocity, you increase the acceleration as the object falls. It's not just the velocity that changes, but the change in velocity, the acceleration is changing. It accelerates and accelerates and accelerates. It's keeping the foot on the gas pedal. And you might already think back to high school physics like, wait, no. Because there's only one acceleration for objects that fall. We'll go back to Newton. So let's go through this carefully. So do we find increasing acceleration? So this is a video I found on the internet. This is a pretty good idea, where somebody lets an object fall, and then they have equal spacing right here. They have a strobe light, so you can see it fall, and then you take images. So you can see exactly at each space and time how deep the object falls. And so what you find is something that looks like this. And you can ask yourself, well, does the acceleration increase? And you can look at the prediction by Galileo and René Descartes, and you can look at what you're actually finding right there. And what you find is that the acceleration, the velocity change, is the same at each time interval. The acceleration is constant. So I've tried to put it up here where you see, yes, the velocity increases, but always by the same amount, proportional to the time. So that means that if the velocity change is the same, the acceleration is the same. And that's what we now think of constant acceleration, which is, of course, what Newton said gravity is. So this is wrong. This is correct. The velocity of a freewheeling body increases in proportion to time. So they both got it wrong, and it turns out that way before, Leonardo da Vinci got it right. He wrote it down, nobody knew. And so, of course, both Descartes and Galileo have been told by people before that they were wrong. But in this case, it's not just that both René Descartes and Galileo were wrong. It's actually interesting that what happened after. So I will call this the Galileo-Cartesian mistake because they both made it. And the mistake was that they had a theory. They learned already from the Greeks that objects fall with the proportionality to distance. So that meant that their theory was kind of dictating their science. And interestingly enough, this is often seen as still Galileo's style, to approach science with theory. And you can see how that can mislead you. And so interestingly enough, what Galileo actually did later, we don't know exactly when, but a couple of years later, he publishes this book. And so just in passing, he writes that the spaces passed over in natural motion are in the same ratio as a proportion as the squares of the times. So Galileo became aware of his own mistake and he corrected it in his later writings. Descartes never corrected his mistake. He died believing this. So what Galileo actually did is he reversed this. Because as we all know, he went to the Leaning Tower of Pisa and he dropped objects. He observed. And he changed his mind. So his view is actually later Galileo, that the data should guide the theory, not the other way around. So interestingly, often that is thought that is Descartes' view, but it's the other way around. So this in the scientific literature, the history of scientific literature is often called retroduction, that you look at the data and then you conclude your theory. So the two lessons I take from that. The first one is, when it comes to truth, what Galileo encountered was an attempt at truth by committee. That the majority of people thought that the Earth is at the center of the solar system. And he couldn't go over this dogma. He did, to his credit, of course. And the second one is that in science, what seems to work best is that we don't start with assumptions, don't start with theory, but we start with observation. And the theory has to match the observation, because the risk is if we go the other way, that we go wrong. So science is about overcoming our own ideas. Another physicist who's still with us, Carlo Rovelli's quote. Last poem. This story I like a lot. Sir Arthur Eddington. Sir Arthur Eddington is famous because he made Einstein who Einstein became. And somehow, in doing that, he also wrote a poem, in this case, pretty much about himself. So this is the poem. Or leave the wiser measures to collate. One thing at least is certain, light has weight. One thing is certain, and the rest debate. Light rays, when near the sun, do not go straight. So what is he talking about here? Well, he's talking about Albert Einstein and his theory of relativity. General relativity is the idea that there's space-time and that gravity can be explained by space-time bending or curving. So we all probably have heard about it, and it sounds pretty out there. And Einstein said, yes, but we can test it. Because if space-time curves, then where you see the stars can also be bent. In other words, stars can jump if there's a big gravity body nearby, because then the light will curve around that object. And we should be able to see that in a solar eclipse. Because in a solar eclipse, if you remember a couple of years ago, everything goes so dark that you can see the stars. And it means that if we map the stars that are exactly close to the sun, they should move in position because their light has to go around the sun. Now, at night, they would be where they are. But if the sun is right there, it's what we call a gravitational lens. The light has to bend around this massive gravity of the sun, and you should see stars where you don't see them at night. In fact, you should be able to take pictures of that. Now, they didn't have a solar eclipse in Europe or the US or anywhere for many years. And this is where Arthur Eddington comes in. So he gets money, he gets funding, and he gets the best cameras and everything. It's a really interesting story. If you go there, it's in the jungle and they have all kinds of cameras don't work. But in the end, he gets this picture. And he shows, and it's hard to see in this picture. So as the story goes, it was just a backup telescope. They had all kinds of problems, but they get the picture. And in this picture, you see that the stars aren't where they are. It's an n equals 1, but that was the time before frequentist statistics were a thing. That was seen as enough evidence. You got the picture. The stars aren't where they are. That's why he wrote in this poem that the light bends. And in fact, it immediately put Einstein on a map, who before was still a little belittled. Stars not where they seem. But nobody need worry. That's back then in the newspaper. Now, that showed that relativity is a real thing. And again, Einstein became a superstar right after. And there's two lessons that I want to talk about relativity that are much on my mind. The first one is, let's go back to Galileo. So this right here, remember that Pope Urban had warned Galileo to treat the heliocentric theory, the idea that the center is the sun, as a mathematical simplification rather than physical reality. So he said, why don't you just say that what we see here and here, and so those are drawings from the time, it's the same mathematically. So this would be the model of the Earth being at the center, the geocentric model. So, and that was, of course, exactly the argument that people used at the time, that if you trace how the planets go around our night sky, you do not get a simple pattern. What you get is this really beautiful, quite elaborate geometric pattern. Whereas if we place the sun at the center of the solar system, all of these patterns of the planets, they become simple. In fact, this is a little bit too simple because the Copernican view had to be revised. This is not how we think the planets go around the sun. It looks this way. It's elliptical. That's what we found out a little bit later. But that still seems more simple than what I showed you before. And so a lot of the idea that the sun, not the Earth, is at the center of the solar system was a parsimonious explanation. The math is more simple. And along comes Einstein. Now, the theory of relativity, why is it called the theory of relativity? It's called the theory of relativity because what Einstein finds out is that motion is relative to an observer. There's no absolute motion, if you will. Motion in the math, physically, is defined with a reference point. So everything has a reference frame. And then people immediately said, well, wait. So if everything is relative, then what Pope Urban said, that if you say the sun is at the center, it doesn't move, or the Earth is at the center, it doesn't move. That's just two reference frames. That's just the same way of saying the same thing, because the motion is relative. And so this was brought up to Einstein's, in this case, special relativity, and he finds the exact same thing. In fact, let me quote you Einstein's response to that. He writes, the two sentences, the sun is at rest and the Earth moves, or the sun moves and the Earth is at rest, simply mean two different conventions concerning two different coordinate systems. Pope was right all along. So in fact, there are lots of programs run by NASA for getting the trajectories of satellites that use the geocentric model because some things are easier to compute this way. And it works because it's mathematically equivalent. But we also have a false notion about falsification. We think that science has to falsify, or statements have to be falsifiable in order to be science. And that leads to these absurdities of when I say 2 days from now, all humans on this planet will die. Is that falsifiable? Yeah, just wait 2 days and see what happens. Does that make it science? The moment you add 3 bodies into the heliocentric view, you can't compute the orbits for a long period of time because of the 3-body problem. They become incomputable. In fact, we do not even know whether our solar system will forever have this because of the inherent chaos in a multi-body system. And we can't compute this for long periods of time. That's why people get nervous about these asteroids that we're talking about. Not because they could hit Earth, because they could introduce tiny little variations that could cause the whole system go chaotic. But we do not know if the universe has a center and where it's at. It's arbitrary reference points. Okay, but more bigger than that, I think science can neither prove nor falsify, because it unfalsifies. We falsify things, and then we later on find that was wrong also. So what science, I suggest, does is that it reduces or enhances the likelihood of theories being correct corresponding with the current evidence. So that's a strong Bayesian approach. I'm not going to go too deep into that, but what science really does is it tells you, given the evidence, this theory is more likely than that theory, and that can be done quite rigorously so using Bayesian formalism. Okay, last thing, real quick, because this bothers me a lot. This is also interesting that Einstein was really unhappy that his theory went down as the theory of relativity, because what he noticed is that people use it to say everything is relative. Now, there's a logical flaw in this. If I say everything is relative, then I'm making an absolute non-relative statement. I'm saying everything is relative. So it's one of these statements that if you apply it to itself, you end up in paradox, incohesion. So whenever somebody says everything is relative, they're saying, but what I just said is not relative. And so Einstein was very much aware of that. And he was bothered because, of course, this would be his main equation for general relativity. That's an absolute truth law. So he very strongly believed what we call in realism, that science is not our subjective storytelling about the world, but what we find are absolute laws of nature that seem to dictate not just our lives, but everything in the universe as it revolves. And so what he thought was that his theory was actually not a theory of relativity, but of invariance. That what his theory would actually show is what doesn't change as we change perspective and use different reference frames. Okay, so long story short, to wrap this all up. Here are the lessons again. So I think from Fermat, we can learn that formal theories predict something inconceivable. Then we should ignore our intuition. We should go by the evidence. From Newton, we can learn that mathematical formalism trumps, and here I'm going to borrow from another physicist. Woolly words, they are inferior to mathematical formalism when it comes to how we describe the world. From Maxwell, we can learn that mathematical descriptions, in fact structures, if that is what math describes, may be all that science can provide. And abstract mathematical objects seem to best describe the universe. These fields, they are just abstract objects. They're not made out of something. If you want to irk a physicist, you ask him, what is a field made out of? And from Einstein, I think we can learn that potential, not currently feasible tests demarcate science. So if somebody says, here's my theory, we cannot test it right now, IIT, that doesn't mean it is pseudoscience, because it can be done in the future. If I can say that I can see if the stars move, we have to wait for a solar eclipse, it doesn't mean the theory is 6 years, for those 6 years, pseudoscience. And of course, physics may be relative in the Einsteinian sense, but it still assumes absolute truth. So even though there's a lot of this pointing towards the direction that the measurement, the individual knowledge of observers matters in how we approach the world, we still believe there's a world out there for us to understand. And then lastly, by Galileo, that phenomenology, and by that I mean your own perception, your own observation, is the starting point of all science. I reckon that if the whole world would just be made out of waterfalls and rocks, even, let's say, butterflies and flowers, there would be no science. For us to do science, it takes individual people in their first-person experience to experience things, put numbers on it, that's what we call a measurement, and then we can take that into mathematics. Everything published in science started with somebody observing these measurements. So what Galileo seemingly did by saying that the Earth is not at the center of the universe, so hence humans should be outside of science. Let's pretend that science is free of humans. We have to humble ourselves and remind ourselves that when we do science, it's not about the objective truth, but what we try to understand about the truth. Our ignorance is built in the cake. So when we do science, we always have to take into account the data that we at this point have. Future generations might have data that we just don't know, and it might change the view of science. And of course, truth is not found by vote, no committee, and even experts may be wrong. I think that is something we can learn from Galileo. Or maybe the one thing that you might want to take away from all of this from Galileo is that be careful who you deem a simpleton. So I started out with the summary, what might be the difference or the similarity between science and poetry? And so I think that, yes, a sense of wonder is core motivation. The fact that we find rules or fascinated by rules, lawfulness, precision, mathematics seems to be similar. Structure, form, the way that we put our wording, notation, symbolism, mathematics seems to be that we find in both. Both challenge our conventions and force us to expanding what we think about the world, expand our horizons, that light might take the fastest path, not the shortest. It makes, and I believe that's the strength of mathematics, the ineffable communicable. Obviously, I struggle to explain to you what a field is, but I'm not the only one. And it might allow us to explore what lies behind our experiences. Obviously, I showed you radioactivity is not something you can directly experience. Maybe years later, you might die of cancer, but we can't hear it, see it, smell it. But science shows us there's this world out there that goes beyond our senses. Now, the last one that I put down when I started this talk and when I put this talk together is maybe what both science and poetry are trying to do is to find the why behind everything. But I think when I went through this talk, at the end, I came up with, when it comes to the why, I think I didn't give you any why. I think that I gave you a lot of things I learned from this exercise, but why wasn't it? Everything I talked about was that science explains the how things work. And so sometimes the how is satisfying for us to seemingly explain why things are. If I say, why are the mammals on this planet the way they are, then I can explain how they came about by evolution, and it seemingly gives us a why. But of course, I can keep asking, why is this a law? I can always ask why. The why never ends. So I actually think that when it comes to science, that what we find in the end, what we learn from physics, is we get equations. And in a way, equations are funny. They're tautological statements. They're saying this is this. F equals ma. And that seems to be the most foundational statements we have in science. So what science really gives us at the end is, these equations. And maybe they explain us how, but they don't explain us why. So the why, maybe, we have to leave up to poetry. And so with that, I want to show you my second favorite poem by another scientist, Henri Poincaré. All that is not thought is pure nothingness, since we can think only thoughts, and all the words we use to speak of things can express only thoughts. To say there's something other than thought is therefore an affirmation which can have no meaning. And yet, life is only a short episode between two eternities of death. Conscious thought has lasted and will last only a moment, and he ends with this beautiful sentence. Thought is only a gleam in the midst of a long night, but it is this gleam which is everything. With that, I'll leave you for the rest of the day. Thanks, everybody.